Okay, please go ahead.
Hi, everyone. Welcome to the discussion today. We're going to be going over some reinforcement learning, getting ready for Revisited Rainbow for next week, which is a new paper in the last couple of years talking about sort of efficiency and cost effectiveness of publishing reinforcement learning, especially in academia, in sort of underrepresented sort of means to be able to publish. So you don't have to be in any of the big computing labs or need upwards of $1 million to $5 million to publish one paper. So today we're just going to be doing a very high-level overview, going into some of the reasons why we do reinforcement learning, and then talking about some of the different flavors of algorithms, and then going a little bit deeper into DQN. So to start, what is reinforcement learning? And it is a real mathematical formalism for learning decision-based making or decision making. And it's an approach for learning decisions making and controlled from experience. So here we have consequences, observations, and rewards, sort of a very illustrated example with the robot in the world, or we have some kind of dog learning as you give them a food reward. As many of you may have had a dog over the over quarantine, this might be a new thing you're trying to learn. But we can also use this in sort of inventory management and different types of robotics. And so to compare it with standard machine learning, usually we're given some distribution X and Y. We want to learn to predict Y from X. This usually assumes that we have IID data and that we actually know our ground truth inputs. However, in contrast with reinforcement learning, the data is not IID, and where the previous inputs or the previous outputs will influence the future inputs. We don't necessarily have ground truth, or only that we know if it succeeds or fails. Specifically, the real crux of reinforcement learning is that we know the reward and we define sort of what the reward will be. So it helps us do and handle unstructured environments. So sort of we have an image input here, we feed it through our network, and we can have a delineated class potentially looking for what potentially is in the picture, where we have a probability of potentially a dictionary of output probabilities. Or we could potentially be looking for different types of dogs, exit signs, etc. It also is a formalism for behavior. So a lot of times people use this in games and decision making. So here we have an example of backgammon, where we have an agent learning how to optimally find the correct action to use in this state. Or we have more of a continuous output where we're trying to have a bipedal walking and trying to use both force and sort of physics to figure out what the optimal sort of actions would be given the specific state. Additionally, we have Google DeepMind doing Atari games as well, and that's one of the big leaps that reinforcement has had in the last decade. So what is deep learning, RL, and why should we really care? So in end-to-end training, we sort of have these classic standards of going from features to mid-level features down to a classifier, where deep learning is an end-to-end training. However, with standard reinforcement learning, we don't necessarily know where more features might be, or if we should have a linear policy input. However, we still would like to have an end-to-end training with an action given a state. And so what does it mean for sequential decision making? So we have perception in sort of an action. And so what we would like to do is, given the picture, we would like to feed it through our network, have some probability of what it might be, and feed it through a network to take another action given a new input. This way, we would want to do more continuous learning to try to be able to have the full network go in cycle. So for an example of robotics, we have the observations, where we get the state estimation with the vision, the modeling predicting, the planning down to the low-level control, and then with the actual controls that it has to feed itself. So here we have an example of a robot trying to tip some kind of contents of a glass into another glass. And so this is just a very illustrative example. Where we also have a second type of robot, where they have a highly specialized visual cortex or motor cortex. And this is more or less where reinforcement was learning in the early stages. We're trying to model classic neuroscience and trying to use terms essentially that are very common in neuroscience to try to bolster more of the terminology. But essentially, it is trying to do sort of a full loop of both actions visually and some kind of movement or new action in the future. And so these deep models allow reinforcement learning to solve these complex problems end to end, which is the real crux. We want to be able to have one image or an input be able to decide from our model what's going to happen next. And so why should we be studying this now? What is the importance? Why haven't we been studying this since the 60s? Is because we've had big advancements in deep learning, advancements with reinforcement learning, especially with the advances of Atari, Google DeepMind. Some of these different companies have poured loads and loads of money into trying to figure out how to even advance the computational complexity and the computational compatibility, sorry. And so with that, we have several papers helping us, or back in '93, they started to allude to why these can be better, and it's naturally integrated into a regular AI networks. There's experience replay, which was a big thing that came about, which we'll talk about. Instructive training instances by human teachers, so we are able to have more examples on imitation learning. We have hierarchical learning, where we have different types of ensembles that could potentially learn various features, and then a lot of it is non-Markovian environments that having a memory.
Can I ask, sort of pick on a word there? You're
Sure.
saying why should we study this now, but you're referring to 93, 95 textbook and paper.
Yes, so there are review papers out there that are coming out right now which is why I really wanted to do the paper that we're going to talk about next week, which is revisiting rainbows. Unfortunately, what we've been seeing is that it just takes too much cost to be able to train on either large GPU farms or even like TCUs. And so what really the crux of reinforcement learning is right now, especially with self-driving being so prominent in sort of even the zeitgeist, this is a huge problem, especially with training models in trying to figure out how to make them more efficient and or just better toy problems for us to train on. Does that make sense?
Yeah.
Great. And so these are some examples. We have the Atari games, like I was saying, Beating Go. There's a documentary on YouTube that Google put out where they actually document the process of going in. I can't remember his last name. Lisa Dole, thank you. Lisa Dole, who was the reigning Go champion at the time, and it was a four games that the algorithm won, where one game he didn't, and there's just some very interesting things in there as well. But that was one of the big leaps and bounds from that. So let's get into some terminology and notation. So here we have the example that I have from the Tiger, where we have an observation T. This is going to be our image, where we're going to have some pi, where this is going to be our policy. And so we say this is a policy because it is an observation, or is an action based from an observation. Here, A is going to be the action, O is the observation, as noted. And so we want, at time T, we want to see what action to take, and then put that back into sort of the policy to be able to see what kind of corrections we need to take. We have sort of the graph diagram here of how the observation actions, and then the state of the action will be what is being fed back into the algorithm. I'm going to pause here if people have any questions.
So observation, so you're assuming some kind of a causal relationship between S and O, right?
Yes, absolutely.
But it is noisy as well. So the state is not directly available to the agent.
Well, for here, we're saying that it is available to the agent. There are different types of algorithms that you can have sort of environments that are hidden to the actor, but essentially the state and the action are a pair that create the policy.
I just wonder why do you need O? Usually it's state to action, right? When but now you have an observation on top of the state, so you're not like this diagram is telling me, at least, maybe I'm interpreting it incorrectly, that you're not accessing state directly on like the action. At least the policy is accessing state only through observation. And yeah, so but if S2 to O2 or whatever, S to O is noiseless, or like O is S essentially, or equivalent to S, then we can just say, yes, I know, the agent knows the state.
Yes, and especially this is coming down from imitation learning, where at least we have both the observation and the actor at the same time, giving us the training data. So essentially, since we don't have ground truth that we're working with, we need to have both the observation and the state to be able to feed back into the network.
So what is state then in this example on the screen now?
The state here is going to be, or the state here is the
current location of the car, right?
Yeah, the state is the current location of the car. Yes, exactly, Elroy.
The current location of the car where? On the screen or on the track that we know how the track looks?
So since this is a time-dependent observation, it's going to be where the car specifically is at that given time. So it's the time point is the state.
So the state, you know the track, and you know where on the track you are right now located, say XY coordinate. And in addition to that, you have 8 megapixels of your observation on the camera.
And I think the state is also kind of the world around you. And in this case, you would probably limit the state towards everything that you can logically see, because the state generates the observation. So like in this case, the state would be the world at exactly that time, but obviously you can't, induce the whole world from one observation of the road. So normally they would kind of say, well, it's limited towards what you can logically see, what you would also be logically able to see as a human. So the location of the car plus where the trees are, where the other cars are on the road, where the lines are on the road, and kind of everything that's
but no, we're not modeling that, Eloy. We're not modeling that. What you're saying is
but that is like for reinforcement learning, that is the state. And
it's a philosophical notion. I'm asking more about mathematical specifics. What are we using as a state here? Which a state is a vector, right? That's represented as a vector. We don't know what the tree is. We just get the input as the image is the input. And yes, a tree generated that image, light reflected from that tree and so on. But it's not the state for us because states should be fully observable.
It doesn't have
the
to be.
observation
In this
a
case, it's
subset
not.
of the state.
It's not a subset of the state, but yeah.
It's just a noisy observation of the whole world, right? Like you can look at.
No, I get what observation is. I don't get what state is. Is state something that we work with, or it's just a philosophical abstract notion that, oh yeah, it's the world that generates the observation, and let's work with observation.
It depends on the application.
So here, given the observation, so given the observation and the action with the policy, you create the next state. And so in the current state you're in, it is going to be from the previous observation and action. So here in at least the little diagram at the bottom, if you have an observation 1 or O1 given some policy with the action 1, it'll generate to state 2. Here we are already in state 1, and we can take the probability of the 2 states given the next state, and that is going to be our probability distribution going from state 1 to state 2. And so state is
okay, but I don't model the states, right?
You don't model the states, no.
Yeah, then it's a philosophical sort of abstract notion. Yes, I made a change, the world changed, but I don't keep the world in memory. I don't need to keep the world in memory. No. And
right. But for example, the paper that we talked about with world models by Schmidhuber, they don't try to model the state directly, but they try to get enough information from the state to be able to predict the information it will need at the next state. So then you have like a world-based model. So that's what they call the paper, is kind of trying to not directly model the state, but model something that is good enough for you to reasonably predict what is going to happen next. So that's like, you have like 2 types of reinforcement learning, right? So like directly from the observation towards the action, and from the observation, you try to sort of get a world model or some idea of like a derivative of the state, like, and then base your action both on the observation and the idea of the state.
Yes, but as long as we understand that S here is an abstract notion and we don't need to worry about it, there will always be a wall or another factor, another variable. I don't know if
but the state will always be dependent on the action, right? So if you look
Yes.
at the, I mean, at the next slide,
yeah,
we are
that
seeing
is
the
clear. Some abstract state unknown
correct,
to us.
correct. So
Yeah,
even
but
so
we
at
can
that
stick
particular
in- Go ahead.
right. So at that particular when we were seeing that particular image, right, where it was showing a car at that track. But like let's say another example, if the track is going to move to left or right, at that time the action will change, and according to that the state will also change. So it's not kind of an abstract variable. It basically it will be telling you like where the next set of application needs to be built upon. So that's so it's not really a abstract variable here. It's an important one, I see.
Actually, there's a button. Sorry, I think it is abstract. Okay, so from what I'm hearing, it is abstract, and we do not model S. We can model S directly by what Eloy said, inserting something here, a simplified model, but we mostly rely on observations.
Right, I agree that in essence it's abstract, but for some applications you can assume that you know the whole state. For example, if you have a stationary robot and you know exactly the location of the arm and like everything about like kind of the world that it operates on, you can assume that you have the fully observed state. And then in that case, O would be S. And that's also what you see on the right in the diagram. Like sometimes if you have a fully observed state, you can assume that O equals S, except for when we saw the car, that's a case where you do not have a fully observed state. And then you need to work with derivatives of the state or predictions of what the state is at that moment, I think.
So if I'm starting from scratch, what will be the initial value, or like what will be the initial what will be the initial value of S in that case? Like if I'm starting from scratch, if I've just started observing something and I've just given one set of action. So at that time, if the agent doesn't know anything, so that time what will be the state?
The state could be potentially random, or the environment that you're in. So potentially this could be lunar lander, where you're starting at some fixed X and Y with zero thrust in all directions.
Yeah.
And so that would be your initial state. As you move on into potentially taking an action like a left thrust, the physics will then work with the environment, and the state will then change. You'll have a different position where you're potentially using. So that is going to be your new observation, if that makes sense.
Well, it's easier to think about games, right? In a chess or alpha or the Go game, the state is your arrangement, and there is no observation. I mean, they're equal. You know where each pebble is.
Exactly. I think that's a beautiful argument. Like if you have a chess game and you just input all the positions of the pieces, you have a fully observed state. But if you have a camera and you look at the board, that would be more of like a non-fully observed state, and then you need the O specifically, and O is not equal to S.
Yeah, there's some noise, and your camera may be misfunctioning. You can take white for black. Or
and your like gripper needs to be in certain locations, and you may not know exactly what. So yeah.
So if we have the state, why do we need the observation? Like, why don't we just use the whole state?
Because
when we have the
you can't put the whole world in memory. Would be my biggest argument.
Well, I think Usman is asking about the chess game, say, we have the state when we can put it into memory, right? But
yeah, let's say we're just observing all rows on the chessboard besides like the leftmost or whatever. And so that would be a partially observable environment. And so that's why we would need an observation of the next state rather than having the full state. I know I'm kind of repeating Elroy, but does that make sense?
Yeah.
Great. So we've gone through sort of imitation learning, but let's talk about the reward function. So which action is then going to be better or worse? And so here we're going to have some reward function based off the state and the action. And so we can define this as a Markov decision process. And it'll tell us which is going to either have a higher reward or a lower reward. So this helps us when we're thinking about how to potentially retrain the algorithm over and over. We want to maximize the best reward. So we're going to try to make the reward as high as possible given the state and the action. And so going through some more definitions, we have a Markov chain here where we can define some S where it has the state space and the transition operator. And why do we call this an operator? It's because it's acting on both the states and the actions. And so that's why we have this transition from going from S1 to S2 or S3 or S2 to S3 here, where they're going to be Markov independent from state to state. Going on to a Markov decision process. Hopefully this is a review for a lot of people, but we're going to have some action space as well. And sort of the diagram here below shows us as we move from one state in action to the next state in action given the transitions. And so here, Richard, going through the reward function is going to be the cross between the states and the action is going to be the reward. And so here, like we were just talking about, where we don't necessarily have the observation space equaling to the full state space itself, we have the partially observed Markov decision processes, which will not go into very many of those algorithms, but this is just to sort of hopefully clear up some of the ambiguity. But this is sort of the way that we think about in terms of notation and diagram. And then I'll pause there if people have any questions about notation.
Okay, well.
Sure, great.
Yeah. So the good thing about Zoom is like I see everyone all the time. Now I have to.
Yeah, I can't see everyone, so I'm just counting to 5 in my head if I ask for questions.
So the question is, the way your reward function is formulated as the product space, it's as if it is defined at each action, right? You're in one state, you made an action, and the reward is defined. But for games, reward is only defined when everything is done, only at the winning or losing position. It's not defined at each action. Or is reward just like kind of multiplied, percolated to each of the board states in the game that happened, or it's divided through them, or?
It depends on how long you want your episode to be. So when we section off how even playing games will have different episodes of how long each episode should be. So in terms of a chess game, it could be all the way to completion or halfway through the game if you think that there's going to be a winning state or not. But it really depends on how you define what your reward is. Is winning going to be 1, or is winning going to be a reward of 200? Is hitting their queen going to be a reward of 10? Is losing your queen going to be a negative reward of 50? And so it really depends on how you define your rewards, and how potentially you can operate with the different types of algorithms. Does that make sense?
But the way you formulate it here in notation is every state has an associated, every state and action pair has an associated reward, which is doesn't look like true, right?
Well, no. So it's going to be the every state in action pair is going to give a reward for that specific observation. And so you then total that at the end of each episode, and then you can use that to potentially either feed it back in, or there's different things with experience replay, or you only take during hyperparameter tuning. So each state action does have a reward given the actor. Yes.
When you make a move in chess, you don't know if you won or not. What the reward
No,
is.
so you will still get a 0 reward for potentially not taking the game. It's just how you define your rewards. So that's the difference between having a algorithm that will say if you win or not, that's going to give a positive reward or a negative reward. However, if you define taking a bishop as its specific reward, or losing your own bishop as a specific negative reward, that's a completely different algorithm itself.
So you're saying if I won the game, all of my moves in that game get a 1 positive reward, and if I lost it, all of them get 0 negative reward, because eventually they led to.
Yes, and so you'll be operating on each game to game, whereas the other one would be operating on just the negative reward, or on each move action. So it's just a difference between how you define the problem you want to solve.
Thanks.
Great. And so the goal of reinforcement learning, as we were talking about, is the expectation of trying to find the correct policy over the sum of all of the rewards. So here we're saying we have this world example we're going into it, feeding into our state, which we give it to our network, where we give it a certain policy, we take states and actions, and then feed it back. And so what we're trying to do is trying to maximize the expectation of the reward. And so this is more formal of what we're talking about. Here's a little block diagram of what we're trying to say. Given a policy, state, and action, we're going state to state in this state. With the
here you would probably say observation, right? Instead of
yes, this would definitely be an observation. But this is getting less to partially observable. I think I kept this presentation more as sort of a either fully realized world or not. I can't remember. But sort of another sort of visual depiction, given a state action, you have your probability of going from one state to the other with the policy, and sort of going through some of the actions just to see visually. And so there are a couple different types of reinforcement learning algorithms where we're trying to either have policy gradients where they're directly differentiating the above objective function. And so here, that's pretty much very vanilla flavors of reinforcement learning. However, the value-based is where we're trying to estimate our Q function, or the quality function that we have of the optimal policy. We'll get more into that in a little bit, but the actor critic is going to be sort of a mix between the both of them, and then model-based reinforcement learning is we're trying to estimate the transition model. So used more for planning, game-based, or even real-world examples where they're very microcosms of environments such as a robotic arm, or where you have the physics very defined in your setting. And so the state action marginal is where you're going to have this P with the state and action. This is going to be more or less the calculating the transition between state action 1, state action 2, state action 3. And so it's there, but we're also very concerned about the stationary distribution. So what if our transitions, we have infinite transitions, or we're in a continuous space? Do we actually converge to a stationary distribution of actions that we could take? And so here it's, we're saying that we have some u, we can take the eigenvector here, which is going to always be 1, which exists under the regulatory conditions. And so this basically says we can potentially get to a stationary distribution given some infinite amount of transitions. That way we can get to the discrete case here that changes our function, where we can estimate the policy given the reward function with a state and action in the limit as transitions go to infinity with law of large numbers. And so with the expectations and stochastic systems, here we either have a infinite horizon case or the finite horizon case, but mostly we care about expectations. So if the reward function is not ever going to be smooth, because potentially in a given car, we're going to have different options of, we don't necessarily want to reward ourselves for staying on the road and then falling off the road at the same time, because we'll have sort of an equal observation of both. So we want to, we could potentially do some reward shaping. However, there can be some very vicious connotations to that, and the triad of issues that can happen with reinforcement learning. But if our expectation will then be smooth based off of the rewards that we implement. And so some of the anatomy of this is the very basic anatomy of a reinforcement learning algorithm. We're going to fit a model and estimate the return. We're going to try to improve the policy and then generate samples to then cyclically go through this. If we go through the illustrated example here, we're just trying to find the highest gradient given the given data, and we're going to do policy gradient to try to search throughout the system and find which one is going to work the best. Here we find a system of equations that such fit the this neural net, and then we backprop through the series of functions to train our policy given the state to get the correct action through the system.
So when you say generate samples, you're actually like exploring the world, actually running and
yes.
driving in your car.
Yes, so whether or not we fall off the cliff or actually go around the bend will all happen. And we hopefully are able to model all of those things to be able to see that if we get to the curve, we don't want to take a right, we actually would like to take a left and stay on the road rather than falling off, as we've given this a negative reward. And so going through defining the Q function, this is our quality function that we say, given the policy of our state action pair. And so this is going to be the total reward from taking any action T in state T. And so it's the expectation given the policy of the reward function given the state action pair. Where the value function here is going to be the sum of the expectation of this policy given the state itself. So we want to see what the value of that state is in turn. So given some expectation of a state in a policy, we want to maximize the value given a state. And that is the big crux of the reinforcement learning objective. And so when using these Q functions and value functions, we have a couple different ideas that we could use. So if we are given a specific policy, pi, and we know that the Q function here, we can improve our policy by setting the state action to 1 if we are maximizing our Q function. And this is saying that this policy is at least good as our maximum policy or even better, but it doesn't matter necessarily what our policy is. Where contrarily, we can compute the gradient to increase the probability of taking a good action. So instead of updating the policy, we would be updating the probability of taking a good action. So this is saying if our Q function is bigger than our value function of the given state, this is as a better average to be able to modify our policy to increase the probability of taking a better action given our Q state. So I want to pause here to ask if there are any questions between policy, action, state, and the Q function.
I sort of have a general statement question about
Sure.
the previous slide. And like, so, I mean, basically up until this point, I have not assumed that we were talking about deep reinforcement learning yet, because you haven't really distinguished between the two as far as I recall.
Yes.
But since you used the term backprop on the previous slide, I guess.
Sure.
That means we're starting to talk about deep reinforcement learning, correct?
Yes. And we will be getting into that here shortly too.
And what is the differentiable part? I mean, like I've seen deep reinforcement learning used in like a few contexts, and it seems like there has to be some sort of way of measuring the quality of your results, and like using that as the differentiable part. Would it be accurate to say the policy is the differentiable part, or what?
So the difference between standard reinforcement learning and deep reinforcement learning is the types of networks that we're able to put into this to fit the model and estimate. DQN specifically is the first flavor of a lot of deep learning nets, and SARSA is another one. But all they sort of coin because of DQN is just the network is very long, or it's taking deep neural net architecture to be able to train the Q function. The Q function specifically is, let me pull up my notes to make sure, I apologize. The Q, I want to make sure I get the verbiage right. The DQN specifically is a learning-based notation. It's the state action value function of a policy that measures the expected return or discounted sum of rewards. And so here, it's impractical to represent the Q function in a table containing all the values and action pairs, because usually in classical reinforcement learning and even temporal difference that Richard Sutton did in the 80s, specifically he was generating what rewards or what the Q function generates given the state and action, and has that in a table. What deep reinforcement learning does is it estimates that Q table and where we're going to be choosing the action given the certain state. Does that make sense?
Okay. Yeah. But so what? I guess my question though is, what are you backpropping on? Like, what is the equation that needs to be differentiable? And what properties does it need to have?
The equation that we're going through is still this Q function, but we're going to be estimating the state action pairs. I guess this is still going to be, I guess this still does need to be differentiable. And I believe it's just how you set up either your network that you're loading into this algorithm, because or the way that it's sort of computing how to get to the Q table.
I also sometimes think an easy way to imagine this is some of the best models in reinforcement learning right now, although they're not very interpretable, is to just have an observation, which is obviously a vector, and an action, which is a certain size vector as well. And some of the best models that at least were named in the rule-based model from Schmidhuber were all just a neural network that mapped O to A. It was just like kind of like a classifier almost. You just take an observation and you just map it to an action state, and that is differentiable because you can say that if you know what the best action would be in that case, then you can differentiate that because you can take the difference between the predicted action and the actual action. For example, in like games, you can do something like that.
I got you.
Not really, not for the actions. In the games, like the Q function of value, you can maximize.
No. But for example, if you have a teacher model, for example, if you're teaching a computer to play chess like a human being, and you just take like Karporov's games, you can just literally do whatever Karporov did is what you should do as a computer as well. In that case, that you can train it like that, and that's the simplest, like the most simple way, I guess, of having a differentiable.
Okay, but then the formalism in this talk is mostly just to structure the conversation. It's not actually used, right? You're just training a supervised model because you have the actions and you want the model to be. But I think, William, you're asking about objective functions. So I think objective function is this Q function. Given a state or given an observation and an action in the model that Eloy was talking about, you want to maximize the final reward or total reward, and that's your Q function is trying to model.
Mm-hmm.
Okay.
Yes. Great. Great. And so the types of, we've gone through these. And so the types of model fitting that we could do, or model-based reinforcement learning algorithms we can do, is to potentially have no policy and to optimize the control primarily continuous spaces. Like we said, to do either backpropagation to optimize over the actions, or even have the discrete case where we do Monte Carlo tree searches, back propagating gradients into the policy as well, which does take some tricks to make it work. But there are also ways to learn the value function here with dynamic programming and definitely doing some convex or linear convex optimization and generate simultaneous experience from model-free learners. There are also value-based functions as well. Sorry, I'm working with two computers. I apologize. Where we're also learning to try to fit either V or Q, depending on the algorithm and how you set up your environment, where you're trying to then maximize over the Q function. And then there's also direct policy grading algorithms where you're improving the gradient during your policy iteration to potentially explore and search as well. And there are parameters that you can put here to either increase the discount of exploring more or exploring less. Actor Critic utilizes both flavors. However, these start to become more difficult to train and tune as you need some very specific connotations when trying to parameter fit, especially when you're trying to fit V, Q, or even the gradient that you're trying to improve. And so some comparison in sample efficiency. Really, how many samples is good? How many episodes do we actually need? Whether you're on policy or off policy, these are going to be really imperative to how you set up or how long it potentially might be to learn a given model. And so with an off policy, you're trying to improve the policy without generating new samples from that policy to be able to explore in potentially a more quote unquote real world example, or at least experience types of action or types of observations that might not necessarily happen in an on policy model. And so just to give you a little example on sort of the efficiency, whether or not you use different types of model-based or even on policy, off policy, we would want to use potentially not necessarily less efficient algorithms, but they're faster to compute in potentially simpler problems that have less complex less complex behaviors could be a lot easier. For example, cart pole, which is just a cart with a pole, and I have the video later, where it's just trying to balance it, is going to be a lot less complex than lunar lander, which has 4 thrusters on either end trying to land in a very specific place on the moon. And so the wall clock time is not the same as efficient. We all know that. And so does it converge? And if not, what to? This is sort of where we define what the reward is and what success actually looks like. And so convergence doesn't actually need to happen if you're reaching a potential reward of 200 in lunar lander based on the actions that you have. In a continuous space, this does not converge. And this is specifically because we're not necessarily using gradient descent, because we're trying to estimate the Q learning or the Q table, which is a fixed point of iteration. And so once you have your model, you're not necessarily converging to the optimal point for the learning itself. It could potentially be one of the best learners, but it's not necessarily guaranteed to converge. Yes, and so model-based reinforcement learning is not necessarily optimized for reward, whereas policy gradient is a gradient descent, but is often the least efficient due to the exploration costs. Value function fitting, it best is used with a Bellman error. This is not the same as expected reward, but at least at worst, it doesn't optimize anything. This is in contrast to the model-based reinforcement learning, which we've been talking about, where the model minimizes the error to fit. This will converge because we do know the model that we're trying to fit, but then there's policy gradient, and there can only be one that actually performs gradient consent on the true objective. So as we've been talking about, there are some common assumptions that you have to either take into account or disregard depending on the algorithm and the situation that you're doing. Fully observable is what we've been talking about, generally assumes that the value function fitting method, but it can be mitigated to adding some recurrence. So that means that you're able to see everything at least once is one of the assumptions, which could potentially not be the effect. Episodic learning, often assumed to be purely policy gradient methods. So this is just learning over and over. So the difference here between learning how the chess game is either won or lost, or the difference between using the rewards on each action that you're taking given the state of the board. And so this is one of the differences where you have to define that, or even the smoothness of the function that you're trying to fit. Either it's going to be continuous or a discrete. And so some examples of the value fitting functions, we have Q learning DQN, temporal difference, fitting value iteration, but we have policy gradient like reinforced natural policy gradients, actor critic algorithms, we have AC3 in SAC, and then the model-based RL algorithms that use a lot more dynamic programming and convex optimization is DYNA and then guided policy gradients. And so with examples like this, we have Q learning here with Atari. That is not the playable video, but with DQN, to try to jump into it, we basically have the idea here. It was developed in DeepMind in 2015, and it was able to solve a wide range of Atari games. And the algorithm was developed to really enhance the classical RL algorithms with Q learning and deep neural networks as a technique with experienced replay. Q learning was based off of the notion of the Q function, as we've been talking about with the state action pair. We're trying to estimate the ideal function of Q star as the maximum return that can be obtained by starting from observation S and taking action A following the optimal policy. For most problems, it's really impractical to represent this Q function as a table, especially in a continuous state. given an action. Instead, here they try to train the function approximator, such as a neural network with given parameters to estimate the Q values. Here we have yi is called the temporal difference target, or the TD target, and yiq is called the TD error. Rho here represents a behavior distribution, and the distribution over the transitions S, A, R, and S prime, collected from the environment. Note here that the parameters of gamma I are fixed and they're not updating. In practice, we use a snapshot of the network parameters for very few iterations, just instead of the last time. And this is called the target network. Q-learning specifically is an off-policy algorithm that learns that the greedy policy of the action while using a different behavior policy and acting in the environment and collected data. Behavior policy is usually the epsilon greedy policy that selects the greedy action with probability 1 minus epsilon in a random action with probability epsilon to ensure good coverage of the state action space in total. Here we have experience replay, and to avoid computing the full expectation of the DQN loss, we can minimize it to use stochastic gradient descent. If the loss is computed from the last transition, this will reduce the standard Q-learning. This specific Atari DQN calls the experience replay to make the network updates more stable. At each time step the data is collected, the transitions are added to a circular buffer called the replay buffer. Then during training, instead of using just the latest transition to compute the loss of its gradient, we compute them using a mini batch of transitions sampled from the replay buffer. This has two big advantages. It has better data efficiency by reducing the transition in many of the updates, and better stability using uncorrelated transitions in a batch. Here is just sort of a quick example using the Bellman operator optimality equation. And we have sort of these red arrows over in the side. And suppose we're trying to find the value of the state with the value of 6. And this is in red. And we can see that we get a reward of -1 if our agent chooses Facebook, and a reward of -2 if our agent chooses to study. In order to find the value of the state in the red, we'll use the Bellman optimality equation for the state value function. Considering the two states, they have the optimal value, which is going from the average, and then maximize both the action, which chooses the one given the maximum value. So from our diagram, we can see that going from Facebook yields a value of 5 for our red state, and going to study yields a value of 6. So we maximize the two over which we have us gives 6 as the answer. Now we would solve the Bellman optimality equation for large MDPs. In order to do that, we need dynamic programming, algorithms like policy iteration or value iteration, which we sort of covered last time. And so how do we sort of test and use different types of toy algorithms? So this is just the pendulum problem, where you're trying to get the pendulum to not swing all the way around. We have sort of different spider walking mechanisms that you can use to program. Lunar lander here is another example, just to try to visualize. And this is the classic cart pull problem, where you're trying to keep a long pole on top of the cart itself. And so, will my slide transition? Great. And so just from a little quick example on what DQN is actually doing in Lunar Lander, here we have the parameters to the left. This is sort of the typical homework that you would do in a reinforcement learning class, where you're taking your function and trying to estimate the different parameters over, of course. I have all these comments here, but the biggest ones that you should really think about is sort of the discount factor, or the gamma here. And it really controls how you explore over time. And so when you do, this might be common sense too, but when you explore hyperparameter search, especially in reinforcement learning, you want to look in a log scale, especially as some of the parameters might necessarily be very finicky in a very small range. And so here, at least with as you start to learn the Lunar Lander, and I don't have a great video of this, but if you have a gamma that's too high, you're going to potentially get a floating agent that's just going to hover over the reward, because it is still maximizing the effect, but it's not necessarily learning to get to the full maximum reward of landing in the square. So sometimes it'll depend. And then the graphs that I have to the right are examples of how you train the reward. In this problem, we're trying to maximize a reward of 200 with a variety of different parameters. You get negative 200 if you fail outside of it. If you're you take some reward if you do less thrusters, and so this is just an example of that. Oop, same video. And so the different flavors that we have of DQN are double DQN, where it'll be able to mitigate the overestimation bias while decoupling. And these are, we can talk about these next time. I'm looking at the time, but these are going to be what we talk about in the next paper using the Minotaur environment, which is essentially taking these various environments that OpenAI has set up and the Atari games and translated them to smaller environments where it is actually efficiently able to be put into a small CPU or a handheld laptop. And so this way you don't need the massive server farms to potentially be able to compute and get the same empirical examples and observations that you do from the original paper. And so we'll be talking more about these flavors and why they matter and what kind of improvements that they make next time. But I will pause here. I believe we have 6 minutes left if people have further questions. I know I kind of bulldozed through that last section.
Thanks, CJ. Questions? Anyone online? Anyone in the room?
I don't know if this is a question so much as just a spurring off or a talking point. I often wonder with reinforcement learning what sort of intersections there are with online learning, especially you mentioned DQN and sensitivity to these hyperparameters that you choose, which is like a hard issue to solve with online learning. Could you speak to that at all?
Yeah, so I guess with reinforcement learning, we're trying to find a model that will correctly be used in time. With online learning, you're trying to get the examples and be able to change your, at least the transition space. So I guess we're trying to, more or less with reinforcement learning, we're trying to figure out the queue function specifically and find that state action table of events, whereas in online learning, you're going to be updating that over time. So with, I believe, a lot more of the reinforcement learning, you want to find an agent that will be able to act accordingly in the given environment. So there, at least from my high level thinking, theoretically, online learning is more or less used to train reinforcement learning models to a point where then reinforcement learning will, or those reinforcement learning models will then be more or less fixed if they're not training better queue tables. So for example, in a Tesla car, they're getting more examples of the observed universe given the actions. However, they're still working from a fixed policy and a fixed algorithm. It just depends on whether or not they're taking that new information and feeding it into the algorithm to potentially update the queue table that they're working with. Does that make sense?
Yeah, totally.
Ilya, maybe you can bring up your point. It's harder for those of us in the room to see the chat because.
So I said in the chat, I said, I personally think role-based reinforcement learning has some really interesting work on learning representations from time series. For example, TJ mentioned temporal difference learning, and that could be interesting when tweaked, obviously, to neural data. I personally think that could be interesting. I've looked at it for myself, for my own project. It's obviously not like a plug and play. You need to change it a little bit, but for example, predicting future neural data for MRI time series, for ICA component time series, or for EEG could lead to better representations or representations that take into account the dynamics maybe of the neural data that we have. And I think there's a lot of interesting work in this field because they also need to be able to predict the world, kind of like how does the world change, and then you can take a more informed action.
Good. Yeah. anything? Yeah, well, I'm thinking of reinforcement learning as a way to learn from sparse reward, like sparse signal. It's very hard to set up a supervised data set where you have everything labeled. And so sort of if we can marry it with semi-supervised learning and things like that, when you only have some labels and use them as rewards, so you can translate them to other areas. I don't know if that research has been done already. It's been used already.
Yeah, because I know it really depends on at least the quality of observations you have as well. And that's why that's the biggest difference between the off policy and the on policy. But I'll have to think about that more, and I can come with a better answer next week as well.
Yeah, well, thank you so much. That's nice and a good idea to have a mini series. We'll see how all that, I'll try to digest. I promise I will do my best effort. To everything you spoke about today, and we'll see how it translates into our next meeting on Friday next week.
Yes, and this is definitely like I don't know, 10 weeks of a course trying to compact it into an hour. So there's definitely more to talk about here as well. If people have questions after the slides are posted, happy to jump on that as well.
Well, we're used to that harsh tortoise to this kind of behavior. Yeah, thanks. Bye-bye.
Great. Thanks, guys.